So you always draw your coordinate axes like really tiny in the corner of the page just because your teacher tells you to do that, just so you can align a positive and negative direction. But it's much more powerful than that, and I'm about to show you why. So this is what they mean when draw your coordinate axes. Like, it's not just for a positive, negative direction. What if you don't memorize the components of the force regarding to a particular problem? Now, when I was in AP1, this is a banked curve. And let's just do it with friction just to jazz it up a little bit, right? APC kids, you already know what it is. So this is basically, I memorized the components for this because I didn't really understand why. I just knew that, oh, the y component of the normal force is going to be Fn cosine theta, and the x component of the normal force is going to be Fn sine theta. But I actually didn't know why. I was just told that, and I was like, okay, I'm going to memorize this for the test. But it's physics. You got to understand everything. So this is why you draw your coordinate axes. So what I'm going to do, I'm going to draw it smack dab in the middle of the center of mass. So the 0, 0 point is going to be the center of mass of this thing. I'm going to draw it really, 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 really big. Okay? So before we get started, let's think of a force that we want to break up into its components. So, you know, y'all always draw this tiny baby one. So, oh no, the normal force is not aligned because it's like this way, and my axes are vertical and horizontal. So basically, it deviates from this vertical axis by some angle, but we're going to break it down. So if this is theta, this is perpendicular, right? 90 degrees. This is some other angle, which is 90 minus theta, which is, let's call it phi, right? Not theta, basically. So this is a vertical angle with this angle. Therefore, this is going to be phi. This is 90 degrees, and therefore, there's only one angle left. This is theta. And since this is a vertical angle with this angle, this is theta. So this is our normal force, right? Now, what if I bring this vector out, let's say right here, right? So if I go like this, this is the normal force, right? You're going to notice that it's like a hypotenuse in a right triangle. It has components to it. It's got a leg here, this is the y component, and a leg here, this is the x component. I'm going to indicate this by saying it's called Fn sub y, and this is Fn sub x, for x component and y component respectively, right? And we said this angle is theta. I showed you all the geometry, guys, 8th grade stuff, or 7th grade if you're, you know, took it big brain in junior high, but like, okay. So this is theta. Therefore, we can say cosine of theta is the adjacent, it's right next to it, it's adjacent to it, over the hypotenuse, which is Fn. And therefore, multiply both sides by Fn cosine theta is equal to Fn sub y. So the y component, as I said earlier, of the normal force with regards to this problem is Fn cosine theta. And we just proved it doing geometry. And then the y component is going to be dealing with sine, so sine of theta is equal to the opposite, so the opposite side from the angle, Fn sub x, over the hypotenuse, Fn. Multiply both sides by Fn. Fn sine theta is equal to Fn sub x, the x component of the normal force. Cool, right? So I'm going to do one more example here just to show you that this thing is legit. So we're going to do it with the friction this time. So I'm going to rub this out since I just showed it to you guys. Come on, come on, go away, go away, go away, go away. All right, so now friction. So say typically when you draw a free body diagram, you draw it at the point of application, right? So draw it down here. But I want this to be as easy as possible. So this is just for demonstration purposes. When you actually draw your free body diagram, please draw force of friction down at the center. But let me just show you another vector here. And we're going to call it force of friction as well. So these two vectors are parallel. Now, I told y'all, y'all can't blame me for this. On the AP exam, draw the force of friction at the point of application, which is right between the surface and the mass, right? I'm just doing this just to show a clear explanation for this. So basically, this vector deviates from this horizontal axis by some angle theta, but well, some angle, we don't know it's theta yet, but basically, this is going to be right here. this is theta, and this whole thing is a 90-degree angle, right? Let me show this real quick. So that means this is going to be that other angle we called phi, right? And this vector is actually perpendicular to the normal force, right? It's actually perpendicular to the normal force, right? So it's as demonstrated by the actual force of friction here, which is perpendicular to the normal force. So we can say, use another color marker here, that the normal force is perpendicular to the force of friction, right? So if this is phi, this angle right here has to be theta as well, right? As I've demonstrated here. So if we pull this vector out and redraw it over here, force of friction, and it has two legs, right? So this is ff sub x, this is ff sub y, correct? And we just proved that this is theta. Now let's do the x component. So cosine of theta is equal to the adjacent ff sub x over the hypotenuse ff. Multiply both sides by f sub f, you'll get the x component of the force of friction is equal to ff cosine of theta. And the solving for the y component, I'll leave that as an exercise for y'all. Haha, I know, right? I'm like a textbook. Exercise left for the reader. Okay, so, but basically, this is the actual purpose of the coordinate axes, not just to draw in some corner of your page and completely forget about it. It has a purpose. If you don't memorize the components on a test, literally just draw a big boy right here, right smack dab in the center of mass of this thing, and then work out your angles, right? So this is the purpose of the coordinate axes, to actually demonstrate how you break up each force into its components when in the context of a particular problem. So hope you all understood.